Myself Dinesh, working as Assistant Professor, Department of Physics. Dear students, in this video, I am going to explain the topic air wedge. Let us see. In this video lecture, I can brief the concept of air wedge. Second one, determination of band width and concept of shape of the fringes. Let us see one by one. Interference due to an air wedge. We have to understand the concept of an air wedge. When two perfectly plane glass plates are inclined at an angle, very small angle theta, a wedge-shaped thin air film is formed between the surfaces. Here in this diagram, these are the two glass plates, plain glass plates. Then the wedge shape arises between the two glass plates here. If such film is viewed by reflected monochromatic light, number of equidistant bright and dark fringes are observed. See here, dark and bright fringes are observed when we can see through the traveling microscope. We can see the fringe pattern like this. They are parallel to the line of joining the two plates. Here, this is the experimental setup. This is monochromatic source, which is originated through the lens, condensing lens, and which is incident on the glass plate, which is inclined at 45 degree, and it undergoes reflection and refraction through glass plate, and finally it is incident on the wedge shape when the two glass plates are inclined to each other. When the two light rays interfere together, we get the interference pattern. Then we can see through, when we can see through telescope, can get the fringe pattern like this. This is the actual glass plates. Here we kept the thin paper between the two glass plates. We can get the fringe pattern like this. This is fringe pattern. Here monochromatic light, yellow, dark, yellow, dark, yellow, dark. Fringe pattern obtained like this. Let us see the expression for bandwidth or expression for wavelength. See here, the thickness of film increases as we move away from the point of contact A. Here thickness goes on increasing here. Consider a point P, this one in the diagram, point P, which is at a distance x from the point A. If a monochromatic light is incident on it, when monochromatic light is incident on it, normally at the point R, it is reflected from the point R and the point P. They produce interference. One of the ray is reflected from the optically denser. It suffers a phase difference of 180 degree or path difference of lambda by 2. Here the ray is reflected from optically denser. It suffers the phase angle 180 degree here in the diagram. Therefore, the true path difference should be 2nt cos or minus lambda by 2, where n is the refractive index. We already derived this true path difference in the thin film interference in the previous video lecture. If r equals 0, then cos r equals 1. When we substitute 0 degree for r, then cos 0 degree equals 1 for normal incident. Then the path difference should be 2nt minus lambda by 2. Let it be equation 1. Let us see the conditions for bright fringe. The path difference for bright fringe is m lambda. Let it be equation 2. From equations 1 and 2, we get 2nt minus lambda by 2 equals m lambda. From these two equations, on equating these two, we get 2nt minus lambda by 2 equals m lambda. Therefore, on further simplification, 2nt equals m lambda plus lambda by 2. Here 2m plus 1 into lambda by 2. Let it be equation 3. Now conditions for dark fringe. We know that the path difference for dark fringe is 2m minus 1 lambda by 2. It will be equation 4. From equation 1 and 4, we get 2nt minus lambda by 2 equals 2m minus 1 lambda by 2. Therefore, on further simplification, 2nt equals 2m minus 1 into lambda by 2 plus lambda by 2. Here lambda by 2 is common factor. Therefore, 2m minus 1 plus 1. Here minus 1 plus 1 cancelled. Therefore, we get m lambda. Let it be equation 5. Now, we want to calculate fringe width or bandwidth. For the dark fringe, already derived, the condition should be 2nt equals m lambda. From the figure, tan theta equals rp by AP. Here opposite by adjacent. Then tan theta equals t by x. Rp means thickness of the film, that is t, upon AP means the distance between the point P and wedge A, that is x. For small value of angle theta equals t by x. Tan term is neglected. Then we get, on cross multiply these two, theta and x, t equals theta x. This is the thickness of the medium. Now 2nt equals m lambda. From the above equation, it becomes, for substitution of t, that is theta x, this becomes 2n x theta equals m lambda. Therefore, x equals m lambda by 2n theta. Let it be equation 6. For m equals 0, 1, 2, so on, various dark lines are formed. For m equals 1, then x1 equals lambda by 2n theta. The same way, for m equals 2, x2 equals 2 lambda by 2n theta. Fringe width, theta equals difference of these two, 1 and 2, first and second fringe, either dark or bright. Then beta equals x2 minus x1. This is equal to 2 lambda by 2n theta minus lambda by 2n theta. Therefore, fringe width, on further simplification of above equation, we get lambda by 2n theta. Let it be equation 7. If the wire is introduced between these two plates at a distance L, from the point A, then it becomes d by L, where d is the diameter of the wire. If theta is small, then above equation becomes theta equals d by L. Theta equals d by L. Where d is the thickness of or diameter of the wire used and L is the length of the wedge. Therefore, from equation 7, it becomes fringe width beta equals lambda L by 2nd. Let it be equation 8. Let us see the shape of the fringes. The locus of points of constant thickness of the film lie along a straight line parallel to the edge of the film. The fringes are straight lines. See here, the fringes are always straight lines. parallel to the edge of the wedge. Since each fringe corresponds to a particular thickness of the wedge, these fringes are called fringes of constant thickness. Here all the fringes are equal thickness and they are equidistant each other. Let us see the problem section. First one, interference fringes are produced by monochromatic light falling normally on a wedge-shaped film of cellophane whose refractive index is 1.4. The angle of the wedge is 22nd of an arc and the distance between successive fringes is 0.25 cm. Calculate the wavelength of light. See here, theta, angle of the wedge, theta equals 22nd of an arc means 20 by 360 degree, which is multiplied by pi by 180 radian. Then it becomes 9.69 in 10 raised to 5 minus 5 radian. Here 22nd of an arc means it is converted into radian here. The refractive index of the medium cellophane is 1.4. The fringe width is given 0.25 10 raised to minus 2 meter. Then find out the wavelength of light used. Here in this case we can use the formula. The fringe width beta equals lambda by 2n theta. So further substitution and calculation we get the wavelength 6.783 in 10 raised to minus 7 meter. Second problem. On illuminating a wedge-shaped air film by light of wavelength 6000 into 10 raised to minus 10 meter, 20 fringes are formed in 10 mm width. Calculate the angle of contact. Here lambda equals 6000 in 10 raised to minus 10 meter, beta equals 10 by 20 into 10 raised to minus 3 meter. Here it is 10 mm width. 20 fringes are formed in 10 mm width means 10 by 20. Then it becomes 0.5 in 10 raised to minus 3 meter. Then find out theta. Here for this problem, you can use the formula theta equals lambda by 2 beta. On further simplification, substitution and simplification, we get 6 into 10 raised to minus 4 into 180 by pi into 60 into 60. Then radian is converted into seconds here. Then it becomes 123.32 seconds. That means 123 means 60 plus 60. That means 2 minutes. And remaining is in seconds, 3.32 seconds. This is the final answer. Third one, in an air wedge experiment, the distance between successive fringes is 1.09 10 raised to minus 4 meter. Calculate the thickness of the object kept between the two optically plane glass plates forming the air wedge. If the length of the wedge is 3.7 10 raised to minus 2 meter and the wavelength of the monochromatic light illuminating the wedge is 5.893 10 raised to minus 7 meter. For this one, we can use the formula D equals L into lambda upon 2 beta. By substituting the above data and calculate, we get the diameter D equals 1 into 10 raised to minus 4 meter. Thank you.